particle, or sorry, particle and antiparticle shenanigans that may or may not be going on with the black holes, right? One of them escapes, one of them doesn't, that type of thing. Like one of the pairs might escape and one of them doesn't. That sort of thing may just allow black holes to be emitting stuff, which then allows black holes to have a temperature. When classically we think that a black hole cannot be emitting anything. A black hole is something that even light cannot escape, so a black hole should not be emitting anything. So this whole explanation of why and how black holes indeed can have a temperature or be having some kind of radiation going outwards is because is understood with quantum mechanics, which Stephen Hawking did. So this is what he's mentioning. Now again, the explanation of how black holes can emit particles and radiation was that one member of a virtual particle-antiparticle pair, so the antiparticle, might fall into the black hole, leaving the other member without a partner with which to annihilate. So it's sort of like that same sort of pair stuff. Basically, a lot can happen with these pairs. It's almost like quantum mechanics gives you sort of a free pass to do with it what you want as far as using up these couples or pairs of particles. And you could just say, well, one of them has fallen into the black hole, so sad, too bad, but the other one sort of escapes, kind of like a divorce of these particles of this pair. And the one that's leaving, that's able to leave, is because that's contributing to what gets emitted from the black hole, and the black hole sort of giving the universe back some stuff, and that's what gives it a temperature. Okay, so the forsaken particle might fall into the hole as well, but it might also escape from the vicinity of the black hole. If so, to an observer at a distance, it would appear to be a particle emitted by the black hole. So this is that whole explanation again, right? One can, however, have a different but equivalent intuitive picture of the mechanism for emission from black holes. One can regard the member of the virtual pair that fell into the black hole, say the antiparticle. Let's say that the antiparticle fell into the black hole. Hi, Dora. As I wake up briefly, I hop to the tab. Here you are, rocking up super late. Hello, it's not super late. It's only 1:19 in the morning. We must have 20 likes. Thank you. I'll pin that. Hardly anyone is here, but it's kind of nice and peaceful, actually. I just want to get my explanations done and then go to bed. Feeling happy. 1:19 in the AM. What? It's only 1. Rock your way. Thank you. Good night. You can listen to this in the background as you're dreaming. Okay, so one can however have a different but equivalent intuitive picture of the mechanism for emission from black holes. One can regard the member of the virtual pair that fell into the black hole, say the antiparticle. Let's say that the antiparticle is the one that has fallen in. Thank you. Night, night. I'll keep it on. Give you the watch time. Thank you. Thank you so much. Good night. So, one can regard the member of the virtual pair that fell into the black hole, the antiparticle, as a particle traveling backward in time out of the hole. So, when you have an antiparticle falling into the black hole, another way of putting it is that a particle has come out of the black hole. When it gets to the point at which the virtual particle-antiparticle pair appeared together, it is scattered by the gravitational field into a particle traveling forward in time and escaping from the black hole, which is pretty dramatic. If instead it were the particle member of the virtual pair that fell into the hole, then one could regard it as an antiparticle traveling back in time and coming out of the black hole. So this time travel stuff may actually be more real and possible when you regard it at that microscopic quantum level, Okay.